welcome to all from on my behalf as well. And the first speaker in this first session today is Lucinda King from University of Surrey, and her topic is onboard digital elevation model implementation. Please, Lucinda, the floor is yours.
2.5 years. I'm just going to get rid of that background because it's annoying. And I've been primarily working on topography, a new reflection point prediction algorithm for reflectometry, which is able to be used over the land surface, not just the ocean. And that's called the topographically accurate reflection point prediction algorithm, or TARP. So I'll be talking a bit about that today and how it's been tested using TechDemoSat-1 data and on board the DOT-1 technology demonstrator satellite. So how do I, there we go. So the reason that we needed to find an updated algorithm is because with reflectometry, as I'm sure many of you know, we have to predict the reflection points in advance because the signals are quite weak. So we have to know where they are in order to track them. And so if you, I don't have a pointer, but point A in this diagram, that's what we would call the specular reflection point. So that's what we're predicting in advance. And then from that, we build up the delay Doppler map. And then if everything is all good, then the peak power, which is coming from the specular point, will be at point A, and that will be centered in the delay Doppler map. And in order to predict these reflection points, we use the positions of the receiver and the transmitter, and then also a model of the Earth's surface. And for ocean sensing, which originally most reflectometry missions were designed for, then using just a mathematical model of the ellipsoid, the WGS84 ellipsoid, that was sufficient as a model. However, for land sensing, where we have to take into account topography and things like that, that's no longer the case. And we can see why that's not the case. If you look at the diagram on the bottom right, it's a very sort of cartoonish diagram, but you can see that the effect of the topography, which is the green line, that can alter the location of the reflection point. And more importantly, it will change the path length and therefore the delay characteristics of the reflected signal. And if we were to just predict those characteristics with a smooth Earth model or the ellipsoidal model, then we would be predicting our delay wrong, which means it's going to end up in the wrong place in the DDM and not at the center. So if you look at the DDM just slightly to the sort of top and right, then you can see that the peak power is offset from the center of the DDM. And if that delay prediction is sort of wrong enough, so if the height difference is great enough, then in some cases it could even disappear from the DDM window completely, and we're not guessing any of that data, which is what we really want. The red box, that's just an example of a windowing we could use for data compression. So that's an 8x8 pixel. So a pixel is a quarter of a code chip. It just shows that if we were to compress it to that much, we could do 24/7 operations on DOT-1. So that's just what's been used as an example. And we can see that for this particular DDM, the elevation difference was enough that if we were compressing by that much, we would lose that data completely. So something needs to be done about this. So I came up with this TARP algorithm, and it is quite simple because it's been designed specifically for use on small satellites, where you have constraints on storage. You can have constraints on processing power sometimes, but also uplink. So as this was going to be tested on DOT-1, which was already in orbit, the uplink of the file was a constraint. And that's because this algorithm uses a digital elevation model on board, and they can be quite hefty. So the way that the algorithm works is that it takes an initial guess. So at the moment, it is dependent on the existing method, which is called the quasi-spherical model, which is based on the mathematical ellipsoid. And so it takes that initial guess and then looks up that location in an onboard digital elevation model. It extracts the height at that point, excuse me, and then replaces the lat long altitude with that height, and then converts it back into ECEF. So as I said, very simple, but this has initially been tested, or it was initially tested in a software receiver on the ground. And the objective of the testing was to see whether this new algorithm could perform better than the existing algorithm, or to be more successful than the existing algorithm at centering that peak power in the DDM window. And the results show that this was the case. So in this top graph, this is a plot of the offset of the delay pixel from the DDM center. So the red is the quasi-spherical. And so you can see that this in general was offset from the center of the DDM. And there is some noise in this because depending on the surface the reflection is coming from, the peak is not always quite clear. But the blue, which is 3 different digital elevation model resolutions all being tested, they all show that they are broadly at the center of the DDM. And another point to note about this red line that with the quasi-spherical model is this is shifted to negative delays relative to the specular point, so into that top part of the DDM, and that's where we often call it the noise box, and that's a method of calibration or to noise ratio. So if there's signals in that region, then that can contaminate our measurements of SNR. So we really want to keep that free of signals if we can. And then if we look to the bottom graph, this is just another representation of the same data, so the offset, but it's a histogram, and it does show quite nicely that in general, the TARP algorithm is placing that peak power at the center of the DDM, whereas there's a much wider spread, including to this top part of the DDM with the quasi-spherical. And what was interesting was, as I mentioned, I tested 3 resolutions of DEM, so 1, 5, and 10 kilometer horizontal resolution, and they didn't really show that many differences in their performance. And I think that's possibly due to the scattering resolution of the actual signals themselves. So as they're all fairly equivalent, then the smallest one was taken forward for testing on board due to the memory constraints, because even the 10 kilometer resolution in 16-bit signed integers was some tens of megabytes. And also this little table at the bottom, so whoops, sorry, go backwards, that the box that I mentioned, that 8x8 pixel box. So I tested the success rate of placing the pixel in the box, and for the quasi-spherical method, that was only 10% of the time, whereas for the TARP method, it was 54% of the time. So it's successful 5 times as many times. Obviously, as an absolute value, that doesn't sound that good because it's only just over 50%. But as I mentioned, this methodology was affected by these more noisy DEMs with weaker peak power, where the method wasn't quite as good at testing where the peak power actually was. But regardless, you can see there is a clear improvement there. And this is just some other examples from the same on the ground testing. So you can see that the peak power was initially quite offset, and then it's down in the center there afterwards. So once it had been tested on the ground, this algorithm was able to be tested in flight, which is very exciting. So it was uploaded onto DOT1, which is a small 17.5 kilogram technology demonstrator built by SSTL. And it has reflectometry capabilities as part of the core DHS onboard computer. And so it was already in flight, as I mentioned, so we had to upload the DEM and the algorithm. But yeah, very excitingly, last year in April, we generated some DDMs using the TARP algorithm, and these were downloaded with some telemetry that made testing possible. And these DDMs, sorry, here were just some of those DDMs, and you can see that they're all quite nicely centered. So testing, the first testing I did was quite simple, and that was just to look at the reported elevation, which was extracted from the DEM on board, and that was reported by a dedicated packet to a control DEM on the ground of the same resolution. And as you can see, so the 10-kilometer resolution DEM on board reported this elevation on the y-axis, and on the x-axis it was the ground. And so for the same resolution, 10 versus 10, it's a nice straight line, as we would have hoped or expected. And then the bottom is just comparing it with a higher resolution DEM on the ground, just to show the difference that the different resolutions can have. So this was being compared with a 1-kilometer DEM on the ground. So we can see it's still broadly, it's a straight line, but there is a bit more noise just coming from the fact that it's a lower resolution. But that all looked good. And then this histogram, so there were approximately, I think, there were 829 tracks of DDMs gathered by DOT1, which were quite a few thousand DDMs in total. And so what I did with those, and those were all broadly over mostly over the land surface. And so I took all of those and I extracted the offset of the delay pixel from the center, and then plotted this onto the this histogram. So you can see that it's, again, broadly in the center of the DDM, with it some spread due to slightly weaker DDMs, or there were some ocean reflections in there and other such things. But yeah, so the testing of the algorithm on board looks good. And this is good because ultimately we want to use this algorithm or the next version of it, which will have some slight adaptations on HydroGNSS, because obviously, as you all know, HydroGNSS is all about sensing the land surface. And so it'll be really important to have that capability on board, especially the coherent channel, which may have been mentioned already yesterday, which is about really tracking well that peak power pixel. And so you must know the location of that in the DDM with a high degree of confidence. So for that, probably the next version of the TARP algorithm, TARP 2, which is already in development, that will probably be important for that. And also the improved data compression that I mentioned with the windowing, that will be important for operational data generation in an operational mission such as this, so we can get the data out to users faster. So yeah, that's me. I hope I didn't take too long, and I'm sorry for being late again. But yeah, so just thank you for everyone. Thank you to SSTL for supporting me with the research. And if you are interested in finding out more about the testing, there is an MDPI paper you can go and find. But yeah, thank you.
Lovely. Thank you very much, Lucy. Some great work there. Do the audience have any questions? There is the question and answer box on the bottom part of the Zoom screen. But if there's no questions, I have some. Question from Maria Krezia. Do you expect also a Doppler offset, especially for very rough surfaces?
Yeah, that's a great question. I think there possibly could be. I don't think it will be as much of an effect. I haven't actually looked into it. I just focused on the delay. But you're right, in future versions of the algorithm, to make it, you know, very, very accurate, then that should be taken into account. But I don't believe it to be as effective. What's the word? As significant as the delay offset.
Okay, thank you very much. Another question is the computational power limitation, which constrains the use of a non-iterative algorithm as TARP v1, still applicable for HydroGNSS?
I think you might be best placed to answer that, Jonathan.
Yes, well, so yes, I can make a comment on that. So yeah, for HydroGNSS, we have significantly less limitations when it comes to the onboard power because we're now using a different architecture of FPGAs. So we still of course do have in orbit some power limitations, but we do have a lot more scope to look at these sort of things. So yeah. And then a question for me, Lucy, is so your DEM at the moment, what sort of coverage over the Earth does it give? Does it give worldwide coverage, or is it?
So the DEM at the moment, it's almost global. The one area that it doesn't cover at the moment is Antarctica, and that is because of different projections. You just need to find a different DEM. But yeah, that's a work in progress, but it shouldn't be an issue to sort of bolt another one on.
And then following on from that, what was the source data for your DEM?
So that came from an EarthEnv product, which in turn came from GMTED and SRTM. So they provided a whole suite of topographic variables, including slopes and things like that, which, as well as elevation, which will be good because in the next version of the algorithm that I mentioned, slopes will be taken into account. So it's nice that they'll come from the same suite of variables, so it's all consistent.
Yeah. Lovely, great. Well, thank you very much. Kimo, hand over to you.
Thank you, Lucinda. Next presenter is Paul Blunt, Associate Professor of GNSS and Communications Engineering from University of Nottingham. And his topic is GPS and Galileo signal characteristics for GNSS reflectometry. The floor is yours, Paul. Please go ahead.
Good morning. Thank you, Kimo, for that introduction. Maybe you can just let me know if you can see my slides and hear me.
Yes,
yep, it's working well. Yep.
Perfect.
Excellent. Okay, great. Okay, good morning, everyone. Yes, I'm Paul Blunt. So I'm an academic at the University of Nottingham in the Nottingham Geospatial Institute. But I've also been working with SSTL and other space receiver manufacturers on GNSS receiver design for many years. And I'm fortunate enough to be also part of the HydroGNSS program, working with SSTL to develop the instrument and to add new capabilities like future GNSS or new GNSS signal capabilities as well. So that's really what this talk is going to be about. Is maybe it's a little bit simpler. So what are we going to talk about? So it's maybe a bit simpler than some of the other presentations you'll see today, but hopefully it gives a useful background in if you're not familiar with the actual signals we're dealing with when we talk about GNSS reflectometry. And specifically, I'll try to talk a little bit about the newer signals, say, because GNSS reflectometry has traditionally used the legacy GPS signals, but we're now moving into looking at dual frequency and also, dual constellation, say, including Galileo signals as well. So we're going to talk about the basic signal properties, the frequency, the modulations, the power level of the signals, and then the coding. So what kind of codes and things are used on these signals. If you're a GNSS expert, hopefully, or signal expert, hopefully this is all familiar to you, or it's a useful refresher, or you just get a warm feeling that that you understand all this stuff. So why do we care about this? So the GNSS signals are designed for navigation primarily, and that's what they've has driven all of the signal design, the modulation and the coding choices. But for GNSSR, they are effectively signals of opportunities. They're signals we've realized we can use with some utility. And yet so the things we care about for reflectometry particularly are the modulation, the fundamental kind of core modulation that's used of the GNSS signals. We'll talk quite a bit about that. as that affects the actual measurements. So those delay Doppler maps that Lucy was just showing in her presentation. The power level, so how much of a return you actually get from the reflected signals and how we calibrate that. And we care about the coding, because that affects how we can actually form the measurements, the quality, the power level of the measurements, and the complexity actually of the instrument for us receiver designers as well. Okay, so just to recap on the signals we're talking about. Traditionally, we've been using the L1 band on the right-hand side here, the blue L1 band GPS signals, but now there's a whole host of GNSS bands ranging from 1.1 to 1.6 gigahertz, including 4 different constellations in there, and potentially a number of these signals can be used for reflectometry. The ones we're going to focus on here are the Galileo signals in the E1 and E1 L1 and E5 L5 bands, because that's also what's going to be used for HydroGNSS. Okay, so basic modulation that we deal with GPS, the kind of, or starting with GPS and then the new signals, there is a modulation of a carrier wave that we show up here with a pseudo-random code. That's a random code sequence. And all this does is effectively we multiply these two together and it changes the phase. Every time the code switches, it modulates the phase of the carrier wave by 180 degrees. And we call this binary phase shift keying, or BPSK. And the effect of this modulation, you can see here, if you just take a carrier wave, the power spectrum is just a tone, it's just a spike, but this pseudo-random code is called a spreading code because it effectively spreads the code, spreads the spectral the energy of the signal across the spectrum. And the amount that spread is defined by the code rate. So if we have a higher code rate, a higher chipping rate, they call it, high rate of this switching of this PRN code, we have a wider bandwidth signal. And we see that in the new signals. So the GPS L1 signal that we've used in the past is a BPSK 1. So that main lobe that you see on the right hand side is about 2 megahertz wide. The GPS L5 signal has 10 times that rate. So we're now having to deal with a signal that's 10 times the bandwidth of what it was previously. And in the receiver, what's going on is effectively the receiver's creating replicas of both this code and the carrier wave and trying to line them up with the received signal. And you kind of see that here in terms of when you line up the code, you get a big spike in the signal there. Oh, somebody's moving a pointer across the screen. I can see. Okay, that's fine. In the center there, we see a large spike, and then we can when the two codes are aligned, and outside of that, when they're misaligned, we get effectively nothing or a small correlation outside of that. That's called the cross correlation. And the longer the code, generally, the lower those values are outside of the point where they're aligned. And if we zoom in on that point where they're aligned with BPSK, we see a single triangle function across the band. Okay, so but that's not the whole story. As we know, we in reflectometry we deal with a delay and Doppler map, so we're trying to line up the code as we had on the left hand side, but we also try and line up the carrier. And if we're offsetting the carrier, we get this kind of sync function that's shown on the right hand side here, that's defined by the integration time that we use in the receiver. And those are kind of noiseless representations. If you actually look at the real signals, you'll see some, plots a bit more like this. And if we show that in 3 dimensions, we can see the actual delay Doppler map. So the whole surface of the correlation with code delay on one dimension and frequency on the other dimension. And generally for reflectometry, we're just zooming in on a portion of this and viewing it from the top. So we then have on the x-axis we have the frequency, the Doppler offset, and on the y-axis the code delay going through the signal. But that's what makes up our delay Doppler map. But in the future, now we've got lots of new modulations coming with, or we already have signals now with Galileo and GPS modernized signals with what's called a binary offset carrier modulation. And here you're modulating that code wave with another square wave. So we see a square wave on the top here, modulating that code. And the effect of that, if we look at the spectrum of the two signals, we had a BPSK signal on the side and our square wave. If we combine those two, what we end up with is pushing the spectral energy over a wider bandwidth either side of the carrier. So we split the signal into two spectral lobes is what we call it. So two lobes, and we shift the energy away from the center. And you can see now in the future, we've got lots of these different modulations coming in with GPS and Galileo, and one that's of particular interest is the red plot in the middle here, because that's the Galileo E1 spectrum, and also the same spectrum will be used for the GPS L1C spectrum that will be used in the next satellites well, due to be transmitted this year, I think, for GPS. And you can see here how they fit in with the existing BPSK modulations, if I include those, but a very busy spectrum now. And the effect of this Bok modulation is now to create, instead of a single triangle, we now have a multiple peaked correlation. So when we look at our delay Doppler map, looking on the y-axis, we would expect not just a single point of energy, but also these other secondary peaks as well. And you could see in Jonathan's presentation yesterday, where he's showing his first delay Doppler maps from Galileo, this kind of three-peaked correlation in the delay Doppler map. And what's important here is that the correlation shape can be very dependent on what the receiver's doing. So whether it's just picking up one component of the signal, two components of the signal, both components, and also the receiver filtering can also change the shape of these individual components of the core correlation that we see in the receiver. So very important to know what's going on in the receiver when you're doing these delay Doppler maps and using the measurements. Okay, so that's modulation. In terms of transmitting power, we care a lot about what the actual gain pattern of the transmitting antennas is. So this is an example of a GPS a gain pattern for a GPS satellite, where the Earth would be in the middle. You can see where it says Earth service, and the edge of the Earth is pointing out at about 13.9 degrees is around there. And all the different plots here are different azimuths. So you can see if you look in a more 3D plot, you can, or looking from top down here, where we've got azimuth going around the plot in this polar plot, we see that the energy also varies in azimuth as well as just the angle to the center of the Earth as well. And in terms of power level, each system defines a kind of minimum level. So here, for example, is the traditional GPS minus 158.5 dB watts is a kind of standard level for GPS, or minimum. But actually, if we take kind of averages across the different blocks, we find that the signal is stronger than that, and also it varies between the blocks. So we have, in terms of knowing what the power level is at the receiver, which is what we care about with reflectometry, both the direct and the reflected, we have variation across blocks, variation across systems, and also the azimuth of the satellite and things like that can affect us. So that was one of the questions I asked yesterday, why we need the direct signal, and that's one of the reasons we need the direct signals for the calibration, as Martin pointed out in the calibration talk, to be able to measure directly that signal level, because the numbers I showed here are just averages as well, and also some satellites have the ability to actively control their power levels. So having this the direct signal and the reflected is very important to us in the receiver. Okay, and then final thing I want to mention is about coding modulation. So in the past, with traditional GPS L1CA signals, you just had a primary code, which was this pseudo-random code sequence, and then you'd have some slower rate navigation data, and that kind of limited how long we could integrate the signal, because we'd have this flipping of the navigation data. In the case of CA code, it was 20 milliseconds. But with the modernized signals, we now have things called secondary codes, which effectively change the sign of so they modulate the primary code. You can see here the epochs of the primary code, and every chip of the secondary code modulating that primary code. So this, if we don't account for this in the receiver, if we don't compensate for it, this can limit the time that we can integrate the signal, which affects well, all of our products, and especially the coherent channel. And if we look, is a table of some of the different sort of coding numbers. So we can see for Galileo signals and then GPS signals, the code lengths, generally the code lengths are much longer. The old CA code is in the middle there, 1023 chips. We have 10 times the primary code and a lot of these new components. And some of them repeat every millisecond, some every 4 milliseconds. But potentially in some of these signals, we now have it being inverted by the secondary code every millisecond. So we need to be able to effectively wipe that off in the receiver in order to integrate for longer. And having the direct signal is very useful for that, because we can effectively, we know what the secondary code sequence will be, and we can apply that to the reflected signal that we're receiving a little bit later than the direct signal that we get. So this is yeah, this is just a feature of the way the signals are now designed, which we have to account for in reflectometry. And generally now the data bits are aligned with the length of this secondary code as well. So when the secondary code finishes, then you have some data modulation. But what you'll notice, there's mention here of I and Q channels, B and C. There's different components for each signal, so there's not just a single component for every signal now. And now we have things called data and pilot channels. So you can see on the right hand side here now, those same signals, the E1B signal is modulated by data. The E1C signal is just a pilot signal which has no data modulation on it. But it still has this secondary code that we need to account for. And it's a feature of most of the modernized signals that you now have these pilot and data components. And generally, this is 50-50 between them, not in every case, but generally it's 50-50 between them. And if we want to get back all that energy for the reflected signal, we need to process both components. And then when we need to process both components, we need to think about those secondary codes and the data modulation. So thinking about how long we can integrate for, and we might be limited by effectively the data period of the signal. So in the case of E1B, for example, the data period is 4 milliseconds, and that can limit us in how long we can integrate the signal without some scheme to wipe them off. But just something to consider, that we need to combine different components of signals now that we have, and also that has the impact of maybe restricting what sort of processing we can do. Also combining the signals, as we saw with the modulation, can affect the correlation shape, and therefore the shape of the delay Doppler map that we receive. Okay, so that's a quick tour of GNSS signal properties. So just saying that some of the main things, this is not an exhaustive review of all the signals here, but just trying to point out some of the main things we care about for reflectometry: the modulation, the power level that the components have and how we can combine the signals, so different components, in order to get all of that power back as well. So thank you for listening. Hopefully I'm happy to have any questions.
Lovely, thank you very much, Paul. Excellent overview of GNSS signals. Yes, so we've had a question. So great presentation. In the context of HydroGNSS, would you then consider its importance to also receive the direct L5 and E5A signal?
Yes, I mean, for the same reason, actually, we know less about the L5, or personally, in terms of published data, we don't really know what the L5 antenna pattern is. We tend to use the L1 and provide a kind of scaling to estimate what the, if we want to estimate what the receiver power is. So yeah, in all cases, it's going to be much better, because we don't know what's going on with the satellites, to have that direct signal where we can measure effectively the power level that we've got coming in, yes, no matter if they're flexibly changing or if we've got variations with blocks and whatever. So yeah, absolutely.
That's once again emphasizing the new ground that Hydro is treading. Another question is, besides GNSS signals, is there any other source of signals of opportunity with potential for reflectometry analysis? For example, signals emitted from GSM towers or radio communication signals?
Possibly. I'm not probably the best person to comment on that. I've not really looked into those kind of signals personally, but yeah, I wouldn't say not. There's definitely.
Yes, so I know that there's definitely someone correct me if I'm wrong. I believe is it the Snoopy mission? They're looking at P-band VHF, P-band signals, whatever band it is. So that, yeah, there are definitely other signals of opportunity that people are looking at.
Yeah, and there's new navigation signals being proposed for low Earth orbit constellations and things like that. So definitely those ones might be good candidates as well.
I've got a question. So you mentioned in one of your slides, there's the box 6.1 component, which is unique to Galileo when it comes to these modernized signals. Do you foresee any interest in that 6.1 component helping us with reflectometry for potentially future hydro work?
Yeah, not really. It's more of a nuisance, I think. Well, if we get that signal back, so there's about 1/11 or 1/12 of the power given to that 6.1 component. So in terms of power, it's not a big hit. But we do need to take into account, if we have a wide bandwidth in the receiver, it will change the correlation shape. So that will change the shape of the delay Doppler map that we receive, and so it may. I'm not sure that it helps the reflectometry resolution particularly or anything like that, but it does affect how how we calibrate the measurement perhaps, and how we process the measurement.
Lovely, great, thank you very much. Yeah, so thank you very much, Paul. Kimmo, I hand back over to you.
Thank you, Paul. Next presenter is Layla Guerrero, Associate Professor from Tor Vergata, University of Rome, and the topic is electromagnetic simulations of GNSS reflectometry. Leila, the floor is yours, please. Go on.
Okay, thank you, Kimmo. I'll share the screen. Okay. Can you see the screen?
Not yet.
Okay. Okay, thank you again.
Yeah? Sorry, we are not able to see your screen yet.
Oh, okay. Let's see. I will. Now?
Yes, it's not yet in the presenter mode, but
okay.
Or the full screen. Now it's okay.
Fine?
Thanks.
Now?
Yes.
Good. Yep.
Thanks.
Okay. Okay. Yes, first of all, I would like to acknowledge my co-authors, Laura Dente from Tor Vergata and Mauro Pierdica and Davide Comite from La Sapienza University of Rome. Okay, this is the outline of this presentation. I will show the electromagnetic basis of savers, which is the electromagnetic tool at the core of the end-to-end simulator for HydroGNSS. I will show some validation of savers against TDS and Cygnus data, and I will conclude with simulations of right polarized and L5 reflectivity, which are the new observables for HydroGNSS. Savers, which means a soil and vegetation reflection simulator, has been developed during about 10 years in the framework of different ESA projects, with the goal of giving physical interpretation to GNSS measurements over land. So the first project was Lemon, that included a ground-based campaign over crops in Tuscany. Then GRASS, that acquired measurements from a light airplane over crops and forest, again in Tuscany. Indeed, colleagues from CNR in Florence participated to both Lemon and GRASS campaigns. And the last project was the one involving data from satellites, and so upgrading the saver simulations to satellites height. Savers can simulate the DDM, solving the radar equation for distributed targets, including the impulse response function in delay and Doppler. The radar equation is extended to the bistatic configuration by means of the bistatic scattering coefficient, which is a function of the bistatic angles, as well as the incidence and observed polarization, and also, of course, of the land parameters, such as soil moisture and biomass, to give an example. Okay, from the bistatic radar equation, we can see that many surface elements or facets contribute to each beam in the delay Doppler map. For each facet, savers can simulate the bistatic scattering coefficient, which has two components, a diffuse incoherent component and a near specular component. The incoherent component is determined by the soil surface roughness at wavelength scale and is estimated through the advanced integral equation model, which is the most advanced electromagnetic model and the most suitable approximation for surface scattering at L-band. There is also a contribution from vegetation, and the attenuation and multiple scattering from vegetation is simulated by means of the Vergata model, which is a model that follows the discrete scatterer approach to solve the radiative transfer equation. In Vergata model, allometric equations are also taken into account to convert LAMP vegetation parameters into detailed geometric and dielectric vegetation description. The near specular component is partially coherent because of the wave impinging on the surface is spherical wave and the surface element is finite. It is possible to introduce a scattering coefficient also for the coherent component. And this term reproduces the image theory and has the advantage to be included in the same radar equation as the incoherent bistatic scattering coefficient. When topographical variations are considered, the bistatic scattering is driven by the local incidence and scattering angles. And this leads us to the reference frames that are defined inside savers. We have a global reference frame, which is a rotated east-north up system. And in this system, the bistatic radar equation is solved. So in this system, we have the different elements inside the antenna footprint, and for each element, the distance and Doppler are computed. In this same reference system, also a digital elevation model is defined at the resolution which is defined by the user. And the DEM allows calculation of aspect and slope of each facets in the global reference grid. Then there is a local reference frame different for each facet in the global reference system. The transformation from the global system to the local system is a function of the aspect and slope. In the local system, also the transmitter and receiver antenna polarization must be rotated, as well as the incidence and scattering directions. In this local system, the bistatic scattering coefficient is computed, and then it is transformed back to the global reference system to be included in the calculation of the radar equation. Okay, going to the comparison with the experimental data, I will show some comparison with the TDS and Cygnus data of reflectivity. Reflectivity is basically the peak power of the DDM normalized to the incident power. You can see here that the definition of reflectivity for TDS and Cygnus are somewhat different, but this is only because the products in the L1 data are different between the two satellite systems. For example, in Cygnus, we have the AIP at the specular point, while for TDS, we have the power at the zenith antenna. As for the simulations, we considered the two different antenna patterns. And in particular, for Cygnus, we considered the antenna pattern obtained as the average of the 8 starboard and 8 port antennas. Here is the first example for tracks collected over Chad. This is a volcanic area with a complex topography, and it is mainly bare and dry. So here on the left, the black dots represent the measurements, the TDS measurements. In particular, this corresponds to the track in the red ellipse over the digital elevation model. The orange line, the continuous line, represents the surface elevation variation along the track. The blue data corresponds to a simulation with savers with a roughness of 3.8 centimeters. And the red line, the red squares report a simulation with a smaller surface roughness. We see that the reflectivity pattern is very well simulated, and we observe that both simulations and data are very much affected by the topography. And also along the track, the variation of small scale pattern can be important. We see that when the surface is, the data collected in the valley are reproduced better by a smaller roughness, by simulations with a smaller roughness. On the contrary, the data acquired over the mountains are better simulated by a higher small scale roughness. Here on the right, the data, the simulations, the comparisons between data simulations and measurements acquired along the 5 tracks in the areas are reported. And we see that small variations of soil roughness along the track can explain the inaccuracies in the simulated value. But we see that the data in the scatter plot have a good correlation coefficient. Here are some comparisons with the Cygnus. Data are collected in San Luis Valley, which is a test site of the modeling group of the Cygnus science team. Also in this case, the photography is quite variable. And again, here at the bottom left, the track-wise peak reflectivity measured are reported in black, and the simulations with 2 surface, small-scale surface roughness are reported. Oops, sorry. Okay, sorry. Again, we see that the main factor affecting the agreement is the uncertainty on the surface roughness. From the scatter plot on the right, we see that good agreement between simulations and observations is obtained with a root mean square error of about 2.6 dB. The larger disagreement is obtained over the mountains, where low signal and noisy DDMs are measured. Let's remain over San Luis Valley. As I mentioned earlier, this is a site of the Cygnus science team. We participated in an activity with colleagues in the Cygnus science team for comparison of the model simulations of the savers simulations with simulations performed with our group in the Cygnus science team. And the results of this collaboration is reported here in the left bottom plot. Here again, a track-wise simulations of the peak reflectivity is reported compared with Cygnus black data. The different colors in this plot report the simulations from models from the Savers model, the model from the Michigan University, and model from the University of South California. On the right, the simulations of the DDM are also a single shot along the track going over St. Louis Valley. Is again reported together with the Cygnus DDM here on the rightmost plot. We see that the three models provide similar results, reproducing reflectivity values, topography effects, and DDMs reasonably well. Let's move to Flores. Here is a track acquired over Congo, over a site with gentle topography and dense forest. Here in the plot, again, the black data are the TDS reflectivity. The orange continuous line reports the LiDAR tree height. We see that when the tree height is low, like here at about 11.5 degrees latitude, the measured reflectivity is higher. On the contrary, when the tree height is larger, the measured reflectivity is lower. This trend is quite well reproduced by Savers, the red dot, and the simulations have been performed considering biomass variables between 85 tons per hectare and 120 tons per hectare. Another comparison, this time with Cygnus, data collected over Gabon, a dense tropical forest with gentle topography. In this case, the track is passing over a large river. On the left, we made simulations and comparison with Cygnus data, considering biomass extracted from the CCI biomass maps. And biomass is variable along the track according to the CCI data. On the left, the simulations do not take into account the water body. We see that there is a slight underestimation by Savers. Instead, on the right, we report the simulation performed taking into account the presence of the river, and we see that the agreement improves, especially in the westward part of the track. The agreement is generally good, again with a root mean square error of about 2.5 degrees, and the largest simulation errors occur at high biomass, where the signal to noise ratio of Cygnus is low. Now let's move to the polarization, the simulation at right polarization. Here on the left, the black dot again are the measured TDS data at left polarization collected over Chad. The green square represents Savers simulations. The orange line again is the surface topography, and the blue triangle are the reflectivities at right polarization, which is about 18-20 dB lower than the left right reflectivity. We see that both polarizations have the same sensitivity to topography. But if we consider the difference between right and left, we have that it is reported by this continuous line on top. It is independent of the large scale and small scale roughness. Furthermore, the polarization difference maintains its sensitivity, the sensitivity to soil moisture. We tried here on the right to simulate a soil moisture variation along the track. We see again that the right polarized reflectivity is much lower than the left one. But if we consider the polarization difference, we see that it presents a counter-related sensitivity to the soil moisture, which is the dashed blue line here. Finally, some simulation of L5 measurements. We see that going from L1, the green simulations, to L5, the red one, the peak reflectivity decreases. Indeed, GPS L5 and Galileo E5 codes have 10-kilometer resolution. Hence, L5 reflections come from smaller area with respect to L1. And this is why the L5 signals are expected to be weaker. These simulations correspond to a situation where incoherent scattering is dominant. So the signal comes from the whole chip size, whose size decreases by about 10 dBs from L1 to L5. However, we performed also simulations for a completely flat area, that is where the scattering is completely coherent. And these simulations suggest that where surfaces are quite flat, like for example, in the case of water in inundated areas, the coherent E5L5 reflection is stronger and may carry useful geophysical information at high resolution. So to conclude, the validation of savers was carried out against TDS and Cygnus data collected over bare soil sites in Chad and St. Louis Valley, forests in Congo and Gabon. The effect of topography is very important and well reproduced by saver. And we saw that reflectivity decreases as the surface slope increases. Savers is also able to reproduce the attenuation of very dense vegetation, and a general good agreement between simulations and observation is reached with the RMS of about 2.5 dBs. The combination of left and right reflectivity can be affected in parameter retrievals, and also the L5 reflectivity can add information at high spatial resolution. And this concludes my talk. Thank you.
Lovely. Thank you very much. Unfortunately, we're slightly running over time, so I think we'll skip questions, but I'm sure if there's questions, please ask them in the chat, and I'm sure we can forward them on to try and see. So,
okay.
Thank you very much.
Thank you.
Kimo, I hand over to you.
Okay, thank you, Leila. We have
Thanks
two more presentations left in this session. Next one will be given by Weiquiang Li from Institute of Space Sciences, Institut Estudios Especials de Catalunya. And his topic is mission consolidation studies using raw intermediate frequency data sets. Weiquiang, the floor is yours, please.
Oh, yes. Thank you. Can you hear me?
Yes.
We can see the Zoom.
I think we're still seeing Leila's screen. I think Leila, you need to.
Yes.
Oh, there we go. I think.
Hey.
Oh, there we go. There we go. Weiquiang, it's yours.
Sorry.
We are not able to see your screen yet.
I think Weiquiang might have dropped out potentially. Let's just see. Okay, then, Kimo, I suggest we skip to Maurizio's if Weiquiang isn't available, and then we'll do Weiquiang.
I think he just came back.
Oh,
Yeah, I'm here. Sorry. So there was something wrong with my Zoom. So now I'll share my screen. Okay. Can you see my screen now?
We can see it. Yes.
Okay.
Okay, perfect. Thanks.
Well, sorry. So my name is Weiquiang Li from the Institute of Space Science, Spanish National Research Council. So I'm the member of the HydroGNSS science team and have been working on different aspects of the mission. So, but in this talk, I'll be only introducing the mission consolidation study using the raw F data. Okay. So in this talk, I will introduce the background and objectives of this study and the RAW-F data and processing strategy and how to apply the RAW-F data in the mission consolidation studies. And finally, I will introduce briefly the status and the future plans of the mission level O RAW-F data processor. So, well, as we know, now there have been quite a few space-bound GNSS missions in orbit, TDS-1, Cygnus, Bufang-1, and Spy CubeSat constellations, DOT-1, and Fengyun 3E. So most of them can process the reflected signal in real time, and the main output is the power DDM of the reflected signal. However, as Martin and Manuel reviewed yesterday, 20 years ago, the early UK DMC mission could only collect limited set of RAW-F data, which are the signal samples at intermediate frequency without any demodulation and real-time processing. So the RAW-F data sets provide valuable input for the current GNSS missions, we have to say. So first, it's consolidated the feasibility of receiving reflected signal in space, even with a lower gain antenna. So second, it provided useful reference for the implementation of the real-time instrument. Finally, it also demonstrated the feasibility of using space-bound GNSS for different scientific applications. So nowadays, the follow-on GNSS missions have been also collecting RAW-F data sets with different features as shown in this table. So with the support of different projects, our group got access to the RAW-F data collected by TDS-1, Cygnus, Bufang-1, as well as a spiral radio octation CubeSat. The sampling rate of the RAW-F data is quite high, from a few mega samples per second to tens of mega samples per second. So we can only collect a few seconds or to a few minutes of this kind of data. With limited size of RAW-F data, normally it's not possible to do any operational applications. But this kind of data provides much more information than the standard level 1 data. For example, we can extract high sampling rate data products with carrier phase information. So we have processed all available RAW-F data and generated the complex waveform as the main data product. So there are more than 4K tracks of the complex waveforms from different missions, and they are available through IEEC Gold RTR server. So by using the RAW-F data site, we have done different types of attempts, like carrier phase altimetry over sea ice, inland water, or even open ocean. And we have also demonstrated space-bound GNSS at multi-frequency and from multi-constellations. For example, on the right plot, we have the waveform at L1 and L2 processed from spiral radio occultation data. And we also have waveforms at spatial B1C and B1I, which are from Buffon 1 RAW-F data. Then the question is, what we can learn from the RAW-F data for the HydroGNSS mission. So basically, with the processing of the RAW-F data, we can support the mission's system design and the instrument design. Also, we can contribute to the main scientific objectives and the implementation of the science data processor. Well, in HydroGNSS, as you know, we will also receive the reflect signal from Galileo E1 to better understand if we can receive the Galileo signals with enough signal-to-noise ratio. We compare the signal-to-noise ratio of the reflected signal from GPS in black, Galileo in blue, and Beidou 3 in red. So then we also normalize the signal-to-noise ratio by considering the impact of the antenna gain, the free space loss, and the wind speed. So finally, we can compare the signal-to-noise ratio from different GNSS constellations. It can be seen that the signal-to-noise ratio of Galileo signal is around 2 dB lower than GPS L1. So to get higher signal-to-noise ratio, we have also analyzed the optimal coherent integration time for the reflected signal. So by using different time of 2 and second, we computed the coherent integration gain. So over ocean, normally we have a 1 dB gain with 4 millisecond integration time. And also we have also selected a few tracks over land and found that by using 4 millisecond coherent integration, we can get even higher signal-to-noise ratio improvement, saying from 1.5 dB to even 3 dB. So I think this may be due to the coherent component of the land reflections. So in the implementation of the instrument, it was suggested to use longer coherent integration time. Well, as Paul just mentioned, there are two components in Galileo E1 open surveys signal, so which are E1B and E1C. So they share half of the total transmitted power. And we would have 3 dB signal-to-noise ratio loss by using only one single signal channel component. So I think the best option is to combine these two channels coherently. So as Paul explained, they are modulated by different navigation database or secondary codes. So we propose a structure to correct the navigation database and the secondary codes before the cross correlation. So in this structure, we only need a few extra output from the direct signal processing. So we also tried to implement this method in our receiver, in our software receiver. So here in these two cases, with the combination in orange and without correction and combination. in blue. So basically, it's clear that we can get this 3 dB gain in signal ratio with this coherent combination. Another innovation of this mission is the coherent channel. So to reduce the size of the coherent channel output, it's better to select only one delay Doppler pixel with a high sampling rate. However, in this case, we need to choose the pixel properly to make sure that it acquires the reflected signal and around the peak of the DDM. So a possible solution is to refine the open tracking model on board and make the specular point pixel in the middle of the DDM window. As Lucy just explained, we can use an onboard DDM model for the computation of the open loop model. So we also tried this approach in our receiver. It shows that with around 6 kilometers resolution DDM model, we can make 95% of the land DDM while located in the DDM window, and the delay error, with the delay error smaller than 150 meters, or half of the CA code chip. So, but it's still challenging for L5 and E5 signals. I think we need further investigate in this topic. So the raw data processing result can also support the mission science objectives. For example, as Tal introduced yesterday, we'll be using the coherent channel for undulation detection. In fact, the feasibility of this application was demonstrated in the frame of Cygnus extended science team study, as well as in HydroGNSS mission consolidation studies. So, but for the development and validation,
Hello, I think we're having a few technical difficulties on Weiquiang's side. We'll just wait a few seconds to see if it comes back. Chemo, I suggest we push on. It sounds like Weiquiang might be having some issues. So I think, yes, if we hand over to the next presenter.
Yes, I think so too. Okay, let's move on to the final presentation, which is given by Maurizio di Bisceglie. Maurizio, I hope you are ready.
Yes, can you hear me?
Okay, yes. Maurizio is from University Sannio, and okay, I'll give the floor to you, please, Maurizio.
Okay.
Go on.
To share my screen. Okay. Can you see correctly?
Yes, yep. Perfect.
Okay. So, okay, this work is a work that is part of a wider investigations that have been carried out with the Weiquiang group that is led by Cinzia Zufada. And so other work will be presented later in this afternoon. Okay, this work is about new method for observing the coherence of the scattered signal in GNSS observations. There is the main need is also confirmed by one observational product that is in HydroGNSS that is considered for measuring inland water dynamics with high spatial and temporal resolution. And these considerations are based on the fact that GNSS reflections exhibits high, strong responses in the presence of water, even in cases where the water is obstructed by vegetation, by some kind of vegetation. So the reason improved, and another motivation is that it's possible to obtain an improved spatial resolution that is achieved because the collection area of the signal is small. It's not the resolution that is good, but it's the collection area, and that is related to the scattering rate in case of coherent scattering, or in case of a combination of coherent and non-coherent or diffuse scattering. So the current GNSS receivers are not properly designed for this kind of measurements, but next generation receivers will do this. And the object is to discuss a metric that has been developed and that is called the entropy of eigenvalues. And this metric is built up to give a measure of the scattering region. So how much the response from the reflected signal is coherent. So the signal model that we consider in this case is given by the sum of coherent components. In the case that we have d coherent components. Each coherent component has a given amplitude. This amplitude depends on, so gamma is an absorption coefficient from vegetation. It also depends on surface roughness as well as on Fresnel coefficient, on incidence angle, distances, and on the phase. So we have essentially we may have more than one coherent component plus an additional incoherent component plus thermal noise. This is the main model that we consider in this approach. So this approach, the entropy metric, is based on essentially on raw data. So we start from raw data, and there is a first processing of raw data in the way that we may form a matrix. The matrix that you can see on the left side. This matrix is composed by single rows of this matrix are delayed waveforms, zero Doppler delayed waveforms. And these waveforms are stacked in this matrix, millisecond by millisecond. So you can see here, so 5,000 milliseconds of acquisitions with 1,000 points for each delayed waveform. And on the right side, you can see the same, but here the waveforms are represented as plots. So you have, in this case, 5,000 so delay waveform superimposed in this plot. So we start from this kind of measurements. You can see that also these measurements are well aligned. So specular points have been aligned very well in this pre-processing phase. After these, the matrix is calculated by some, let me say, standard technique in signal processing. So from the matrix or from a slice of that matrix, we consider a number of milliseconds, not all milliseconds. So for example, a number from 10 to 50 milliseconds in the matrix, and also not all the length of the waveform, but a number of samples around the specular point. And from this submatrix, we calculate the data correlation matrix that you can see, for example, in this picture. And after the data correlation matrix, because the noise is and the incoherent component is correlated, we need to consider a generalized eigenvalue decomposition, not a simple eigenvalue decomposition. You can see here that in a simple, not generalized eigenvalue decomposition, this R0 matrix is the identity matrix. But in that case, we have a correlation of the noise, and so of the incoherent noise part. So we should consider an eigen and generalized eigendecomposition. So after this generalized decomposition, we calculate the eigenvalues and that are represented in this picture. This picture represent so the eigenvalues that are also sorted from the largest one to the smallest one. And these eigenvalues are normalized, such as they are similar to probabilities. And so I mean that the sum of all eigenvalues will be normalized such that the sum is 1. And from this kind of sort of probabilities, is calculated the entropy. What are the properties of this entropy? Okay, the entropy, differently from some other measure exploits both the shape of the waveform, so the shape of the delay waveform, and also exploits the temporal variation of these waveforms in a number of milliseconds, for example, from 10 to 50 milliseconds. And also this metric is also depending on the complex values of the correlations, because the correlation matrix is based on complex waveforms. So includes both shape of the waveform, temporal variation of the waveform, and phase. The eigenvalues are a powerful indicator on how these the energy of the signal is spread along independent directions. And so measuring the entropy have the meaning of understanding how the energy is displaced along the various dimensions. If we have all the energies along one dimension, we have zero entropy. Otherwise, if the energy is displaced uniformly on all the dimensions, the entropy is zero. And so this is the meaning of our case. Also, this metric depends on some parameters, like number of samples, number of waveforms, and there are some constraints to be consistent with the rank of correlation. Okay, we have here some experiments. One experiment is with Lake Okeechobee in Florida, and we can see what happens in some different cases depending on the surface roughness. And in figures A and B, there are two cases of high wind speed. So in the surface of the lake, you can see that the entropy is close to 1. Otherwise, in the wetland zones that are along the border of the lake, we have lower entropy. In figure C and D, it's a case of a moderate wind speed, and in the figure E, which is interesting, it is the case of low wind speed. In that case, you can see that the entropy is low along the water, and this is because with high probability, I think that we have not a very precise measurement, but we have some measurement of the voice in the lake. In these cases, sorry. Okay, sorry. Something is happening. Sorry. Oh, I think it's a problem with PowerPoint. Okay. Okay.
We can see the slide again.
Yeah. Okay. Okay. Sorry for the problem. In the plots, you can see the entropy as compared with the SNR in the comparison in the plots, and you can see that okay, so there is some similarity between measurements from SNR and entropy. One means entropy equivalent, and but perhaps the entropy measure is more stable than the SNR. So there is also a sensitivity of entropy to the wetland type. This is the case of some other experiments that where we consider the type of vegetation that is on this part around Okeechobee Lake, and in that case, there are some different behavior of the entropy metric with respect to different type of vegetations like watergrass, lotus, American lotus, woody, and other kind of vegetation that we have examined. And there are some differences that you can appreciate with the entropy and measurement. So this is another experiment that is made during an hurricane in Louisiana in that happened in the 2017, and the hurricane is in this zone of Louisiana, and we have a better image in this case, where we can see that okay, along the this part of the sea, so the entropy is very variable, but it's in any case very high, close to 1, but became very low in this part of the coast that is perhaps inundated by the waves of the ocean, and also in this part of the island that is also perhaps inundated. So there is a very sharp behavior of the eigenvalues in this case, in this experiment. So now the last part of the presentation is just a consideration about a different method that we call fast entropy. This method has been considered to alleviate the computational complexity of the calculation of the eigenvalues. So essentially, we approximate the calculation of the eigenvalues because we just calculated the largest eigenvalue, so one eigenvalue, with a very powerful method that is very fast. In our case, we use the power method, the name of the algorithm. And then we calculate another eigenvalue that is calculated as the average of all the remaining eigenvalues. I want to point out that we know the sum of all eigenvalues, that is the trace of the matrix. So it is very simple to calculate the first eigenvalue with power method and the average of the remaining eigenvalues. So the new entropy that we can calculate in this case is a binary entropy. So it's composed by two eigenvalues. And in this case, we have a comparison between the full entropy and the fast entropy. Fast entropy is represented with blue plots, and the full entropy is represented with red plots. So you can see that there is a bias, but this bias is quite small, and so it is still possible to have a good consideration of the coherence of the sketch vector. And so the gain in terms of time, this is a MATLAB code, is of the order of 10, depending on the different parameters that we use. And so, next one. Okay, thank you. Thank you very much from the others.
Lovely. Thank you very much. I think, unfortunately, due to time, I think we're going to need to skip questions, but I'm sure that if we have those questions, once again, if I'll ask your questions in the question and answer area, and we can make sure those questions get passed on. So thank you very much. Oh, also, it was unfortunate that we lost Weiquiang's presentation halfway through. We will ensure that is sent round after the workshop, so that work is not so you can still read his stuff. So thank you very much. Pete, am I passing over to you now? I believe I am.
Thank you, everybody, for all of those interesting topics this morning. Sorry about the technical hitch that we had earlier. So that concludes the session. So we're running shortly, a little bit longer than planned. So we'll have a short break. We'll come back at 10:55, please. So 5 minutes later than the advertised on the schedule. And we'll be talking about, we'll be hearing from the potential users of HydroGNSS.